Test 8, we've got a good amount of new formulas, and they were all sectioned. You'll notice, I mentioned this already, that I put a new version of the formula sheet on Moodle. If you haven't, for some reason, looked at that yet, you should open it in Notability now so that you're familiar with it before Monday's test, right? The format of it looks a little bit different. I switched to 3 columns instead of 2. I added more stuff along the bottom. I just want you to be familiar with it. So if you haven't opened it for some reason, just go to Moodle. It's under Documents and Handouts, and open the formula sheet so you can at least see it. But we've got a lot of formulas there for Chapter 8. The positive, or the pro to this, is that those formulas are the same formulas we used earlier in the year, but wherever we saw V earlier in the year for velocity, that becomes omega for angular velocity. Wherever we saw X or Y for displacement, that became theta for angular displacement. And wherever we saw A for acceleration, that has become alpha for angular acceleration. So it's important to know that the formulas that you're utilizing for the most part are not any different from VF equals VI plus AT. VF squared equals VI squared plus 2AX. It's the same formulas. I'm just changing my variables because instead of things moving translationally, sliding up and down, sliding left and right, they are now rotating instead. And when things rotate, the rotation is measured by an angle instead of a linear displacement. And the velocity is measured by angular velocity, how fast it rotates, instead of how fast it slides or moves left to right. And then finally, the acceleration is given as how fast it's changing its angular velocity, instead of how fast acceleration is changing linear velocity. So we see the analogy between the two different types, kinematics on the left and rotational motion on the right. Okay? But the formulas are very similar. Now, some key things to jot down before we go to any problems for today, because I saw a lot of mistakes on things like homeworks and when people were coming to ask me questions that were common amongst many people. So first, theta. What does it always have to be measured in? Radians. It's got to be. Omega. Units. It's not meters per second. Radians per second. And alpha, last but not least. Radians per second squared. So my units are really important. A lot of the time for these types of problems, and I'm not going to make every one of these problems this way because then you would just be converting every problem. But a lot of real life problems, let's be honest, nobody's going to walk around and say, oh, you know what? That engine is rotating at 27,000 radians per second. You don't use that unit. It's not reasonable. So in math, we use it because a radian is a measurement that we're going to utilize. What unit do we use? We use RPMs, which is rotations per minute. So we need to be able to convert. I'm telling you now, you will 100% have a problem where I give you omega in RPMs. You're going to have to utilize it, so you have to convert it to radians per second. And again, rotation to radian is one conversion, and then it's minutes to seconds as the other conversion. So keep that in the back of your mind that we have to be able in this section to convert our units. Convert our units. And anytime we're going to use any formula from Chapter 8, these need to be the units shown. Okay? What other formulas from Chapter 8 didn't involve angles were like S equals theta R or V equals R omega? Those formulas with R and S are always measured in meters. So in these formulas from Chapter 8, we also had variables like R and S, and those units need to be in meters. Okay? So units are really important. Units are really important, as always. So when given a problem on this test, where it says that an object swings through an angle of 270 degrees, well, that's theta. But the unit doesn't match up. but you need to know that radians and degrees are similar units. They both measure angular displacement. So at 270 degrees, what does that look like? Start here. All the way to there. Does that make sense? Okay, this is 180. This is 90. 270. And then the last one would be a full rotation, 360. Now, if you can't remember for some reason your conversion between degrees and radians, it's on your formula sheet. I added it to the bottom. 180 degrees, pi radians. Good. Is pi radians. At this point, from the homeworks, the problem sets, I almost kind of assume you know it, but I put it at the bottom of the formula sheet just in case anybody forgets it, so there's no reason you can't convert. Okay, so pi radians is 180 degrees. You could also think of a full circle. Remember I talked about being 2 pi, and the 2 pi is 360. If 2 pi is a full 360, well, 1 pi is just going to be 180. So if I were looking at rotations, one full rotation is 2 pi radians. One full that's not on your formula sheet. That's not on your formula sheet. But one full rotation, aka 360 degrees, one full rotation is 2 pi radians. 2 pi radians. Remember, 2 pi is just a number. 6.28 ... It's that many radians of measurement per whatever time period, if it's velocity versus displacement. All right, with that said, that's Chapter 8's key points for formulas. I can list them all, but they're all on your formula sheet in front of you right now. Okay, some of them that look a little bit different than what we've used, just so we know where they're useful. This is used for arc length measurements. This is used to relate your tangential speed, or your book might have called that the linear speed with the fishing rod example. The tangential speed is related to the angular speed with that formula. And then the last one was the tangential acceleration is related to the angular acceleration. So these three formulas are kind of new ones, right? Those are the three formulas that are kind of new, whereas the other formulas are all just interpretations of the older formulas. VF equals VF squared equals, or X equals VIT plus 1FAT squared. They're all just rewriting the other formulas with the new variables.
On the right, what is the last symbol?
This one? Oops. This guy right here?
Yeah.
That stands for angular acceleration. Just like acceleration we had for something moving. If I'm spinning something, and then I spin it faster, and then I spin it faster, that means that it is accelerating angularly. Angular acceleration.
So you're just saying tangential acceleration is equal to the radius times angular.
Yep, that's all it is. Absolutely. And the same thing goes for the middle one. The tangential velocity or speed is equal to the radius of the thing spinning times the angular speed. Times the angular speed. And this is telling us if I need to know how much of a path something has swept out physically, linearly, I can figure that out by knowing the angle that has changed in radians and the radius itself. Again, remember, radians per second squared. Okay, so these three formulas are the same if you notice, right? One has to do with displacement, one has to do with velocity, one has to do with acceleration. But they're all r times something. R times angular velocity, r times angular displacement, r times angular acceleration. All of these formulas are r times something to do with angular each time. And they all give us like a linear length. The arc length, the tangential speed, the tangential acceleration. Chapter 13 involves several other formulas. The formulas from chapter 13 that we utilized were first, frequency is equal to 1 over the period. The period of a mass spring is 2 pi root m over k, and the period of a pendulum being 2 pi root L over g. Those were, I think, the only 3 formulas that you had in chapter 13. Mathematically, not too bad. What's the hard part about this section is rearranging these formulas. Honestly, solving for G, solving for K, solving for M, solving for L. That could be a little bit tricky, but with practice, it is very easy. So if you're a little bit confused on how to isolate one of those variables under the radical, you need to go back and look at the videos. We did it in the lesson. We actually solved for K, and we solved for L. So go back and look at the process we took and practice it. Practice it enough, it'll get very easy for you. But the math in this section is not meant to be super tricky. You'll notice that about chapter 13. It's really not. But you need to know what words mean. And what do I mean by that? Here's what I mean. There was a problem in your problem set that a lot of students get confused or have trouble with. And it's the general problem. And I'll give you an example. It's not the exact problem, but I'll say this one. If you dribble about, was the basketball one of these? It was, damn, okay. If, let me think. Ooh, what's a good example? Oh, here we go. If you pluck a guitar string, and it tells you that the string oscillates 300 times in 4 seconds, what are they giving you by telling you that? 300 oscillations of the guitar string occur, it vibrates 300 times in 4 seconds. What are you being given? Frequency, good. You need to know what that word frequency means. And I've noticed a little bit with the problem sets and with the questions I've been getting over the last couple of days that people have a little difficulty with the concept of frequency. Frequency is either cycles per second, oscillations per second, vibrations per second. In basketball, dribbles per second. In science and biology, heartbeats per second. That's a frequency. Anything that is occurring with some cyclical pattern, right? How annoying is this? Isn't it so annoying when the person next to you in class sits there and taps their foot and you're in the middle of a test and somebody sits there tapping the whole time? Well, what are they doing? They're creating some sort of a frequency or a rhythm that makes them feel comfortable. But it has a frequency to it. It's the amount of taps per second. You might not be given that it's 20 taps per second. But if I tell you again that it's 300 taps every 7 seconds, that's the frequency. 300 over second. Taps per, 300 over 7, over 7. Taps per second. Cycles per second. Oscillations per second. They all mean the same thing. How is that different from the period length?
The period length is like the time that it takes for one oscillation.
Good. It's the time it takes for every tap, for every dribble, for every oscillation. So in this case, quickly, 300 over, I should just make it over 6 to make life easier. Let's just make this 6. 300 divided by 6 is 50 taps every second. Now, that's not obviously a person. No human being can tap 50 times in 1 second. As much as you think you're a good drummer, you ain't that good. No drummer, no human drummer is taking 50 drum beats in 1 given second, right? So just so we're aware of that number reference frame. But this is what we've got. So if hypothetically, remember I talked about bugs, right? I talked about bugs and they flap their wings at a certain rate. This is a realistic number. Bugs could easily flap or oscillate their wings 50 times in a second. And that's with the buzzing that you're hearing. That's the frequency of the buzzing that you're hearing. So how long would it take 1 oscillation at this rate? Well, how would you figure that out?
1 over whatever frequency is.
Yeah, you would literally take the reciprocal of this. And think about it logically. Look at the units. Right now, it's 50 taps per second. If I flipped it, it would be the amount of seconds per, and that's what period length is, isn't it? That's why the period and the frequency are reciprocals of each other. That's the reason that they're reciprocals for one another. Okay? M.
So if you were given the 300 times per 6 seconds, could you technically just use that to find the period instead of the frequency?
Sure.
And then like plug that one into.
You can do 6 over 300 and that gives you the period automatically. Absolutely, 100% you can. Okay, you definitely can. And what about, yeah?
Would you switch F and T so you would get T equals 1 over F?
And that's why they're reciprocals of each other. 1 over any number is a reciprocal, right? That's the definition of reciprocal. What's the reciprocal of 2/3? It's 3/2, because you're doing 1 over 2/3, which makes it 3/2. So that's why I said if you take the reciprocal of this, you get the amount of seconds per tap. Well, this was our frequency.
Yeah.
And we're told that the reciprocal frequency is period.
Oh, so it would be 1 over 50 would be your time.
Correct. It would be 1 second for every 50 taps. So that would be like 0.002 or 0.02 seconds per tap. That would give you the actual period. So again, this is what frequency is. And what's another unit for seconds? What's another unit for taps per second? Go back up to frequency. Taps per second. Oscillations, what is it? Hertz, good. So another way of writing this is, 50 hertz. Okay, 50 hertz. And I see seconds per tap, but per tap doesn't really matter. Per cycle, per whatever. That's some unitless value. So really, what are the units of period? Those units are seconds. 0.02 seconds. That's 1 time period. Per tap, per cycle, per oscillation, whatever word you would like to utilize there. All right, that's my spiel about 8 and 13. What do you want to ask about? What do you want to go over? What do you want to... Yeah, go ahead, start.
Or like wavelength?
Wavelength? Sure. Oh, I didn't use that formula. Let me write that formula. So the formula we're going to see here is V equals wavelength times frequency. That was one of our other formulas from that section I didn't include yet. So let's use that formula to discuss what wavelength is. So if I were to look at a wave like this, the wavelength is just simply the distance from one wave front to the other. And if you recall, I talked about the Doppler effect with ambulances. And I talked to you guys about how when the ambulance approaches you, it's like the wave is compressing. And when the ambulance leaves you, the wave is expanding. So what's happening there? When an ambulance approaches you, you hear the siren is a pretty high pitch. And then when it leaves you, you hear a much lower pitch. Because what's happening is this. When the ambulance approaches you, it's compressing its wavelengths because it's physically catching up to the waves. So what's happening is that when the ambulance approaches you, this gap right here, from crest to crest, from each sound wave, is getting smaller and smaller. So let's go ahead and look at our formula here, please. If the wavelength goes down and the speed of sound is a constant, that's the number we've been using. I've referenced it, I think, twice so far. You don't have to memorize it. It'll be given. The speed of sound is a constant, 343 meters per second. It's really not a constant. I mentioned that temperature changes and all these other things change it. But for the sake of right now, the speed of sound could be considered to be a constant. So if the wavelength goes down, what has to happen to the frequency? Bridge? It's got to go up. For this answer to always be 343 for the speed of sound, if I have a certain wavelength and that number goes down, to compensate for this going down, this has to go up. Very much like momentum. P equals mv. If the mass went up, the velocity went down if the momentum was held constant. Same idea here. So what's happening is this. The wavelength of the siren sound when it approaches you shrinks. So take a look at the second wave I'm going to draw down here. The new wavelength is from here to here. The blue wavelength is clearly larger than the green one. So as the ambulance approaches you, It's sending out these sound waves that are getting compressed by the ambulance itself that's catching up to the sound waves. So you see that the wavelength decreases. A decrease in wavelength causes an increase in frequency. And what is frequency really for sound? What is frequency for sound really? What's the word we use in music?
Pitch?
Pitch. Decibels are amplitude. Decibels are amplitude. That's the volume intensity of the sound. Pitch is frequency. So let's talk about that other word, though, that Bridge just mentioned. The amplitude. The amplitude of a wave is the height of the wave. Remember, folks, amplitude is from the midline to either the top or the bottom. Amplitude is not from the trough or the min to the crest or the max. Amplitude is not this full height change. It's from the midline to the maximum value. That's what amplitude is defined by, right here. Okay, the midline to the maximum. And what in sound is amplitude? That's the amount of the intensity, measured in decibels. Remember what I said about amplitude. Amplitude is going to have many different units. For a spring that's oscillating back and forth, what did I say the amplitude was? When a spring gets pulled back and forth, what measures how far the amplitude is? Meters. A pendulum raised up to here versus raised up to a higher amplitude. What measures the amplitude of a pendulum? What units measure the amplitude of a pendulum? Radians or degrees. Either one in that case, actually. Radians or degrees. So what's going to be the amplitude for sound? It's called decibels. I'm not going to quiz you on it tomorrow, but I want you to recognize that I talked about this already. Amplitude talks about energy being carried. The more amplitude, the more energy the wave carries. The more energy I have, the louder my voice is, literally. If I don't give much energy to my voice, it's going to be very low. That's a low amplitude sound wave. Okay, so you need to know the physical meaning of these things. I'm not going to test you on decibels and math behind that. There's a lot of math behind all of that. There's a lot of math involving what is called apparent frequency with what's called the Doppler effect, where the siren sounds higher pitched. I haven't gone into that math here. Okay, that is math that is covered on something like the subject test. But you'll notice that at the bottom of my Moodle page, I put those topics there. I put like the math behind the Doppler effect because we don't cover it in this course. But if you're taking the subject test, you probably want to know it. So it's included there if you want to see it. But you need to know the physical significance of what's going on with waves. So more amplitude, more energy the wave carries. For a sound wave, it just means it's louder. That's all it means. What else? It kind of gives you the idea, or the most idea I can give you now at least, of what wavelength physically is. And wavelength is measured in meters. Okay, it's measured in meters. What else? Questions? Dan?
To go over how to find like the resultant wave.
Yeah, an example of interference?
Yeah.
Sure. So let's look at an example, and I'm going to arbitrate one up here. So let's say that's the first wave. And that's the second wave. Now, if you needed to find the resultant wave for two given wave forms, all you really want to do is add them together. But at certain locations, it makes sense. For example, take a look at where I'm going to point to real quick. If I were to add this positive height to this negative height, either there, or there, or there, is anything going to change? in any of those locations. So at location 1, at location 2, or location 3, if I were to add together this positive amplitude to this negative, this positive to this negative, this positive to this negative, it's not going to change. This is, say, 5, 5, 5 as a height. This is -1. So the resultant is going to be 4 the entire time. So when you're adding together waves, it's important to strategically pick locations that you're going to add. So 1, 2, and 3 don't actually make sense. Location 1 makes sense to add. But 2 and 3 don't really. Now, where else would make sense? Probably right here makes sense to add to here. And then afterward, the value of the blue wave is 0 at all these locations. So if I were to find a resultant wave, I think of this as 5, call this -1. Let's call this height 2. And that's going to match up with the height of this wave right here. So we're aware of why I'm calling that 2. Now, if I were to add the first waves at the very beginning of this, say that at time equals 0, at the very start, I would have 5 plus -1, and 5 plus -1 would yield 4, so my resultant wave in green would start here up at 4. Now, if I keep adding these waves together, it's not going to change. Still not going to change until I get to right here. And when I get to that location, this blue wave is no longer going to play any role. Because what's the amplitude of a wave that's on the axis? 0. So 0 plus 5 is going to be 5. 0 plus 4 is going to be 4. 0 plus 3 is going to be 3. So really, my resultant wave in green can overlay the red wave that entire time. So it's going to look like that. Again, this is going to be -1 plus 5 the whole way, which is 4. And then once this becomes 0, I now have 0 plus 5, which is 5. 0 plus 4, which is 4. 0 plus 3, which is 3. You see what I'm doing each time? I'm overlapping them. Now in this region, take a look. Does the red wave have any significance at all here? So it's pretty much the blue wave plus, so it's pretty much just the blue wave until the red wave has some significance. So let's do that. So the resultant would still be this, until I get to right here. That's where I got to start thinking. Now, at this specific location, I still have, we'll call this -1 for now, make believe it lines up. I still have -1 plus 0, which is -1, right? But then at this location, this is like -2 or 3. But now this wave has some height. So I have to start picking strategic points. So maybe pick a point like this, pick another point at the max, pick another point over here, and then maybe pick another point that's at the end. And then because this flat lines, let's pick this as another point. So I have to look at several instances. So take slices of the graph and add those heights together. So when I look at this slice, let me show you what I'm referring to. When I look at this here, and I line it up with this right here, I could say, well, what's this height, approximately? Approximately. 5-ish, maybe 6 if it's a little more. But let's just say 5-ish for now. And let's say that this height down here is around -4. So I'm going to pick that location. So that's around -4. Let me erase the green so it's not confusing. So if I were to add together the positive amplitude of 5 and the negative amplitude here of -4, +5 and -4 will yield +1. So I can already know that my resultant wave would be like there. Then if I were to add together this location, and again, you would have a grid line behind you. This would be a lot easier, right? If there was grids on the graph, it would be a ton easier than this. So let's say this location is at -3, and this location here is at +3. +3 and -3 is complete destructive interference, which means that at that location, this wave would have 0 height. So along the way, we have to consider that our wave is going to have different heights, and then we can connect those dots with smooth curves. But we have to figure out a couple locations. So maybe I also consider this location, which is 0 height, plus this, Well, that's going to be right on the blue wave itself. And then the red wave has no value after that. So that's going to follow that path along the way. But at this location right here, maybe this is still a height of 4. And this down here is a height of like -6. Take a look where I'm looking. This is 4, adding -6. -6 plus a +4 is a -2. So that might put this part right here. So what I'll notice is that my wave is going to have this interesting behavior. It doesn't need to be perfect, but it's going to probably look something like this. So my resultant wave is this green tracking that you're following the entire way through. Again, I gave an example here on the graph with no grid lines. With grid lines, you can pick specific points where you'll know the exact height, and you could sum those values together to get the height of the resultant wave. Once you have the resultant wave with enough dots, you can just connect the dots like I did right there and get an approximate smooth curve for that wave. Okay? Now this is an example where I'm giving you the two waves on the same graph and you sum them together, as opposed to this, the pulse example, right? If this height is 4 and this height is 3, when these two pulses combine, what's the resultant height of that wave going to be? Simply 1. Okay? A +4 from this guy, a -3 from this wave. As a result, and again, notice I put 3, but this is a wave on the bottom side of the actual axis. It's like having a negative amplitude. So a 4 and a -3 yield a +1. So when these two waves do merge, it'll look something like that. Okay? That middle spot with an amplitude of +1. So that's what I want you to get from destructive and constructive interference. This really does summarize destructive and constructive interference. So not heavy math, but the graphical approach is definitely a little bit of math, right? Simple math, but definitely involves math. And how can you do this to practice? Make up your own waves if you'd want to. Make up your own, draw two shapes, and try to come up with the resultant wave. Maybe on the test I'll give you 2 waves, and I'll tell you to make the resultant. Or maybe I'll give you 3 waves and say, which of the following is the resultant wave and which are the original 2 waves? And you got to be able to figure that out. And it's somewhat obvious. I mean, if I look at this, the only way for this to be the resultant wave, or the only way for this to work, is if this is the resultant wave. And let me explain that. Take a look. Ready? Let's call this a height of 4. If I was adding 4 and -1 together, what would I get? So wouldn't the resultant be in the inside if this was the original wave? And doesn't it look like this is like in the outside? So there's no way that this and this could be the original wave. It just doesn't work. Mathematically, it just doesn't physically work. I can't take 4 and add -1 and yield 5. So already I know that the red one cannot be the resultant. You see what I'm getting at there? So use your context clues. Okay, use your context clues. Use process of elimination. There's only one resultant wave that will work in all instances or in all times. All right, what else? Chapter 8, maybe? Chapter 13, more? What do you want to do? If there's a specific math problem or problems that you struggled with in Chapter 8 or Chapter 13... We got to be able to convert in Chapter 8. Let's show a quick conversion of that. So if I had 1,700 RPMs given in a problem, I have to write this first as 1,700 rotations per 1 minute. That's what that physically means. And let's say I want to convert this into my standard units of radians per second. I want to get rid of rotations, and it's in the top. So I put it where?
On.
And what do I want to get to? What unit?
Second.
Eventually for time, but for rotations, what do I want to get to? Instead of rotations, I want to get to radians. Rotations and rotations cancel, but how many rotations are in a radian, or how many radians are in a rotation? What's the conversion factor there?
2 pi radians
In?
in 1 rotation.
Good. In one rotation. So now I'm in radians per minute. Now I'm in radians per minute, but I want to be in radians per second. Seconds are in the bottom, and I don't want them anymore, so what do? I don't want seconds anymore, and they're in the I don't want minutes anymore, and they're in the bottom, so what do, Em?
Multiply by 1 minute over 60 seconds.
So multiply by something with minutes up top. And yes, minutes can convert to seconds very easily with a ratio of 1 minute for every 60 seconds. And as a result now, minutes cancel in both spots. Which leaves me behind with radians per second. So what kind of a number is 1,700 rotations per minute in radians per second? Let's look. It's this times this divided by this. Again, multiply across whenever you're converting at the very last step. Everything that's a 1 doesn't matter. Unless it's the only 1, then it does matter, right? If it's the only 1 in the numerator, then your answer is 1 over something. But if it's multiplying by 1, it doesn't make any difference. So generally speaking, rotations per minute to radians per second, the number's going to go down. Because you're multiplying by 2 pi, which is around 6, right? But then you're dividing by 60, right? If I look at my last answer, I'm really multiplying by around 6.28 and then dividing by 60. So my answer is going to go down by like a factor of 10, but not. Okay? So it'd be like maybe 170, but not 170. It's not exactly 10 as a factor. So what does my answer become for that if I actually evaluate it, just so we have an idea of numbers? What does that become? Thanks, Prams. Thanks, Bridge, for checking. I see both of you guys in your calculator. What do you got?
178.
178. And again, radians per second. So just so you have a number sense, I can't tell you how many students don't know the difference sometimes between, like, what is a centimeter? What is a millimeter? What is a meter? You should physically know what that size is. So a number sense. So on the test on Monday, when I give you a problem in rotations per minute or RPMs, when you convert it, the number should get smaller if you're going to radians per second. See what I'm saying? You're going from 1,700 to about 170. It's going to go down by about a factor of 10, not exactly. Again, because this is 6.28 and this is 60. Had this been 6 over 60, then the factor would be exactly 10. Number sense. Yeah,
Do you have a problem with like arc length, like as they stay to arc?
sure. Let's say that a crankshaft is rotating, and the crankshaft rotates through an angle of 185 degrees. And the length of the crankshaft is 2.1 meters. In the process of this crankshaft doing this, and let's say the crankshaft is like a plow, okay? So from a bird's eye view, here's the arm of the crankshaft, here's the little spade at the end of the crank. And what's happening from the center, and it rotates, as it rotates through an angle of around 185 degrees, it digs out the soil. And it digs out this ditch in the soil. It creates like an irrigation system. Okay, so the crank arm is rotating and literally sweeping out the soil in that area. Well, maybe the question is, how many linear feet of plants can we plant? How many linear feet, or meters in this case, can we plant? So what they're asking for is the length of that arc, highlighted in red. you're physically being asked for the length of the arc highlighted in red. So if I want to think about this, I could think of this whole thing as a circle. I could call the length here the radius, really. And I can use my formula, S equals theta r. The issue or the concern is that theta and omega and all of those values need to be in radians. So I can go ahead and try to multiply, but I can't use 185. I can use 2.1 meters here, that's fine, because the length of the arm of the crankshaft is the radius, right? It's like a little robot that gives you little spots that you can plant. And these robots literally do exactly this. They move along a path, sometimes along a linear path, and they'll dig out the ground, and as they dig out the ground, they drop seeds behind afterward. And then another robot comes by to fill them in. Humans aren't doing it anymore. It just isn't happening. So this is digging out the ground, and we need to figure out how long is that path it dug out. So we know that we can space out the seeds every 3 inches. Maybe it needs to be another seed because it's a, I don't know, watermelon plant, whatever it is that grows there. So in this problem, we need to use arc length equals the angle swept out times the radius. Well, the angle swept out in this problem is this angle right here. Before you do it, multiply by pi radians over 180 degrees to convert. So this number is 185 times pi over 180, and that'll be units of radians. Because again, degrees cancel with degrees up there, and this will be my value. My answer will be in meters because I'm looking at the arc length. Please, people, after school today, if you have questions on the lab you just turned in that's going to be on this test, come by and see me after school. I can go over with you for like 15, 20 minutes. If you have a question about the test in general, come by after school, but try to come by right after school so I can get right to baseball too. What you would say, that's good. A lot of kids like the pen and heads when they do a really job. You would say like, take scenario 1. When the radius or the length of the string is 0.2 meters, the velocity is 2.86 meters per second. So actually reference here. So it's good that you put that there. So you want to use those things. So sometimes when you're summarizing stuff, you can make like a small table to show that.
Thanks, can I ask you a question? What direction does velocity act?
It always acts tangent to the circle.
Oh, okay.
Tangent to the
Tangent
circle.
to the circle.
Did you put outward, I'm guessing? Is that what you wrote?
No, yeah. I put towards the center.
Yeah, so
it was like center.
think about when you're spinning it. If you were to let go at any moment, which way would it go? It would go tangent to the circle.
Yeah.
So that's the velocity at that instant. But the force and the acceleration is always toward the center.
Okay. All right, thank you.
Okay? Yep.